because our little rocket situation didn't work out, today was the day that you were supposed to turn your report, but you don't have a report. I expect nobody's done anything on it because you had no data, right? I'm sorry that didn't work out. I will work on getting better pads or seals and actually try them before I do this again. What we're going to do today is continue on with what we ended with last class period. So last class period, we were, first we did Newton's synthesis, where I showed you the actual work for how to go from a force to a potential energy. Today we're going to look a little more carefully at the process and see a little more calculus involvement than we did last time. So potential energy is defined based on work from a conservative force. And so far I've defined conservative forces with a descriptive terminology. So what do you remember for what it means for something to be a conservative force?
When the force is, conservative is kind of hard to describe it, but it's like for example, after a collision, the momentum is transferred, but they don't lose energy per se.
Okay, something where you don't lose mechanical energy. Okay, that's correct. What were you going to say, Nathan? Something along those lines, because that was also going to be correct. Other things I said where it doesn't matter what path you take to go from point A to B, it only matters what your position is because it's an energy based on your position alone. So we are going to, on the next slide, see a mathematical definition to help us determine if a force is conservative. Now, something that we have not seen is the reverse of the definition of potential energy. The definition of potential energy is the change in potential energy is minus the work done. But work is integral of force dot distance. And so here I've put the integral of force dot distance. And then I was very specific in saying the force is the force in x direction times the x unit vector, that's 1 in the x direction, plus the force in the y direction times 1 in the y direction, plus the force in the z direction times 1 in the z direction. Do you guys have the unit vector idea down? Does the unit vector, does an x with a little hat or carré over it mean something to you? Okay. It would be the same as if I said like east, north, and up, right? It's just telling you the direction. So east is a unit vector, if you will. It doesn't have a direction to it or a distance to it. It just has a direction. So this is the force in the x plus force in the y plus force in the z, dotted with distance in the x, distance in the y, distance in the z. dx, dy, and dz. Now, when you do a dot product, what does it mean to do a dot product? I think all of you raised your hand when I asked about dot products and cross products. What does dot product mean? It's not just multiply. It's multiply, but it's not just multiply. Multiply the parallel parts. So the reason I broke it down like this is you can say, okay, x is parallel to x. So this could be rewritten as integral from xa to xb fx dx plus integral from ya to yb, didn't need to use parentheses, fy dy plus integral from za to zb fz dz. So all three of these integrals, this one, and this set of three, mean exactly the same thing. The reason we write it with the dot product is because that's by far the simplest way to write it. So it's important to have those ideas in your head of what it means when you see the integral of the dot product. Now the reverse of this, we can calculate the force from the potential. Now this is vectors, so with the vectors things are a little different than without the vectors. So let's pretend, well let's just say we had a one-dimensional situation. So I have change in potential energy is equal to minus the integral of force, I'll take away the vector because it's one dimension, force dx. How could I find the force from this equation?
If you're looking for F, right?
Yeah, I'm looking for the function f. And so mathematically, what steps would I have to take to find f from this?
Take the derivative of F.
Yeah, the fundamental theorem of calculus. The derivative of the integral is going to be what you started with. So if I take the derivative with respect, change colors here, derivative with respect to x, then on the right side, that's going to be minus f. And so I should have minus f is equal to d dx of the change in potential energy. And when I say minus f, we have to keep in mind there were limits here. So this is actually going to be minus f final minus parenthesis minus f initial, right? Since it's going to be at the, yeah. Or more simply, we just get minus f is equal to d potential energy dx. That is getting rid of the delta and the difference between the two spots. So that's how it would work out one-dimensionally. Now we have a three-dimensional problem because we have force dot dx. And so with the 3 dimensions, we replace a simple derivative with that thing that's called gradient. Have you guys seen gradient in your calculus class? Okay, Kaylin, less likely than the other two, because you only had calculus 1. Nathan and Michael?
Yeah.
Haven't seen that yet. Okay, so gradient is a directional derivative. So since we've talked about what x hat and y hat and z hat mean, can you read what that gradient equation is? Like, say in English words, instead of saying x hat, well, maybe I should start with this. Does anybody know what that means? We talked about it the first lecture of the class. Now is going to come up the time when we're first going to use it. So that funny D, partial derivative. Sorry, were you going to say that, Nate? Yes, it looks kind of like a backward 6. That is a form of a Greek, I think it's Greek D, Greek delta, a lowercase Greek delta. There are different forms of it, and they have different meanings mathematically. So that's the form of a lowercase Greek delta that means a partial derivative. And partial derivatives are the easy ones. Just get it out of your head, partial means easy. Partial puts a smile on my face. Because a partial derivative means that anything that you're not taking it with respect to, so for this one, d dx, I'm taking a derivative with respect to x. Any variable that's not x is constant. It doesn't depend on anything as far as you care for a partial derivative. So if I have a function that's x times y times z, normally x, y, z could all change. And so I would have to use the product rule for taking my derivatives. I'd have, derivative of the first term x with respect to x, then times yz, plus x times derivative y with respect to x, times, and so on. But if it's partial, you don't worry about it. Just take derivative with respect to x and everything else treat as a constant. So with that delta meaning partial derivative, how can we say this equation this gradient, we call it an operator. How can we say that in English words instead of mathematical jargon? It's still mathematical jargon when you get down to it, but it's not symbols at least. So what does x hat mean? In the x direction. So I'm going to have in the x direction, what do I have in the x direction?
A certain force.
Well, just inside the red box, just making sure we understand what the gradient operator means. So we have in the x direction something. What do we have in the x direction?
A partial derivative over the partial derivative of x.
Okay, it's the partial derivative with respect to x. So in the x direction, partial derivative with respect to x, plus in the y direction, the partial derivative with respect to y, plus in the z direction, partial derivative with respect to z. So we can read that. So I can find the force if I know the potential energy, or I can find the potential energy if I know the force by using these two math relations. Now, by the way, this is the gradient in Cartesian coordinates. Cartesian coordinates are the ones named after Rene Descartes that we typically call x, y, and z. Not the only set of coordinates we can use. We can use spherical coordinates or cylindrical coordinates, and the gradient operator is going to look different. So is this part here if you use different coordinate systems. Yes, I forgot to silence my watch. Nathan told me not to do that, but I did anyway. Parents, obey your kids. That's the rule you should learn. So, with all of this said, there's one more thing to learn before we do practice problems. So, the one more thing to learn to do is to determine if it's a conservative force. And a mathematical rule is conservative forces have the curl of the force equals 0. And like, what in the world is the curl of the force? It's gradient crossed with the force. What did a cross product mean? That comes from yesterday. What does a cross product mean? Dot product is multiplying the parallel parts, multiplying the perpendicular parts. And we're going to see a little more carefully how to do a cross product here today. Now, using what we've seen, I could write the del as x hat d dx plus y hat d dy plus z hat d dz. So I have that cross fx in the x direction plus fy in the y direction plus fz in the z direction. You know, that's not as easy as it looks in what I wrote. So here's how we actually do the calculation. We do it with a determinant. So I'm going to, well, first I will write over here the actual determinant, and then I'll show an example. So the actual way you do it is, if I have A vector cross B vector, that's equal determinant x hat, y hat, z hat, a sub x, a sub y, a sub z. That's how we go about calculating a cross product. We find the determinant of a matrix. And we need practice with determinants probably too, don't we? If you have a 3x3 matrix, you can use a semblance of the rules that you learned. I learned these in high school. I was going to say grade school, but no, I learned them in high school. If you have more than a 3x3 matrix, you have to use the method I'm going to show here. And that is choose a row or column. It does not matter which, but in this case, it's real obvious that you should choose this one. And then for each one, you take, for each item in that row or column, you take the item and you multiply it by the determinant of its co-matrix. All these words, probably new, right? No?
It sounds familiar. Like the whole matrix determinant.
The co-matrix is the matrix if you take out the row and column of that element. So the thing in the box is the co-matrix to the x in the circle. The x in the circle we call the cofactor. So it's the cofactor times the determinant of the co-matrix. So my cofactor is x hat, and then my co-matrix determinant that's all good except for the next step. Now I move on to the next one. So go on to the next one. I alternate signs. So now it's minus y hat because I'm alternating sign. It was plus for the first one, minus for the second one. And then what's the co-matrix for y? Take out the row that y's in and the column y's in, and what am I left with? Perfect. Notice he took out this row and this column, and so the two things that weren't dashed out, he gave me. And then for the final one, oh, I'll use white. I'll go to red. Alternate signs, so that was a minus, so now I go back to a plus. Z hat, AX, BX, AY, BY. The math writing is much simpler than the math doing, isn't it? When we wrote that we need to find del cross F, it looked pretty simple. But when we get to how we calculate del cross F, it's going to be kind of long. So now let's do a practical example. So we're going to calculate the curl of the spring force. The spring force is minus k, and here I put the force is minus k x vector. If we define our directions right, we could just say that the force is minus kx in the x direction. Right, if we just define x as the direction that we're stretching the spring. So we have that works just fine for a spring. So that's what I'm going to do. So if I'm going to find this curl, then I'm going to have del is a triangle with the point down and a vector sign. I need to write my determinant and what goes in the top row of the determinant. What goes in the top row of the determinant?
Using those two.
The top row is always going to be the unit vectors.
So those will always be the same.
For our cross product, yes. And then what goes in the second row?
What is the name for the symbol on the left?
This here? Gradient or del.
Okay. Del.
Okay, so it's the components of the gradient operator, components of del. So it's going to be, now I don't put x hat, y hat, z hat, I just put d dx because that was the x component, and d dy because that's the y component, and d dz because that's the z component. And then what goes in the final row?
F sub x.
And?
F sub y. Both 0.
Yeah, f sub y and f sub z were 0, right? Because it was all in the x direction.
Oh, yeah.
So now it's time to calculate. So doing what I said before, I'm going to have x hat times the determinant of then I change the sign, determinant of change the sign once again. And now I calculate these. Now, how do you calculate the determinant of a 2 by 2 matrix? Whole lot of math going on today. Well, when we're down to the 2, we take this minus that. So we take d dy of 0 minus d dz of 0. Well, what's the derivative of 0? 0. So that's going to be equals x hat times 0 minus y hat times, okay, what's d dx of 0? 0. What's d dz of minus kx? Remember, that's a partial with respect to z. If it's a partial with respect to z, what does that tell you about the derivative? That x is a constant, and k was already a constant. So what's the derivative of a constant? 0, right? Because derivative is just change. If it's constant, there's no change. And so this is 0 plus z hat. I should have put here, to be real technical, 0 minus instead, just minus. And then here I'm going to have, again, 0 minus d dy minus kx. What's the partial derivative with respect to y of minus kx? Be 0 again, because we're treating x as a constant since it's a partial with respect to y. So that was easy. 0 plus 0 plus 0. So what we found here is that the curl of f was definitely equal to 0. This is true. Therefore, conservative. So we did the test. The reason to do that curl calculation was to test to see if it was a conservative force or not. Now that it's conservative, we can calculate the potential energy of it. Aren't you excited? We actually did this calculation in class a week ago. We said, well, if that's the equation for the force, then I'm going to have the work plus 0 for the y component and z component, because I aligned everything with the x direction like I had done right there. So it was 0, the force was 0 in the y direction, 0 in the z direction, so that's why I put plus 0. And so then it's easy. What's the integral of minus kx dx? That'd be the derivative. So that's the work going from A to B. And we said that the change in potential energy is minus that. So change in potential energy is equal to potential energy B minus potential energy A is equal to minus and so by rearranging this, we just rearrange this to put the signs right. That's distributing the negative sign into the bracket. And we can just read, well, potential energy B is 1/2 kx b squared. Potential energy A is 1/2 kx a squared. Or in general, potential energy is equal to 1/2 kx squared. So we get the general relation for a spring you could always have a plus C for an offset. It wouldn't make any difference because we defined the potential energy by the change. And so if I said potential energy is 1/2 kx squared plus C, potential energy B minus potential energy A would be 1/2 kx b squared plus C minus 1/2 kx a squared plus C. The plus C's would subtract out. But by convention, we say, why would we ever want to put the C there? We'll just put C as 0, make life easy. I just identified potential energy B is going to be the one that has X sub B in it, and potential energy A is going to be the one that has X sub A in it.
It looks familiar to another formula that we've been using. I think it was for kinetic energy.
Well, kinetic energy is 1/2 mv squared, and that comes from integrated momentum, actually. And so I believe we'll be doing that coming up pretty soon. But that also comes from an integral. Yay! Okay, so we were able to do two things here. Number one, to show that the equation for a spring's force is conservative. And once we establish that, then to find the potential energy associated with that spring force. So now we go to something harder, because we hardly ever go from hard to easy. It's pretty much always easy to hard. And so each step is a step harder. What is harder about the general gravitational potential energy, or the general gravitational force?
It's more than just one direction.
It's more than just one direction. Now, the gravitational force is spherically symmetric. Because it's spherically symmetric, well, how do I know it's spherically symmetric? Sorry, Nick. Because my force is only dependent on the radius, and the direction is always attractive. So you have the r hat direction, it's always in the radial direction, and it depends on the radius. So because of that spherical symmetry, we generally work with the gravitational force using spherical components, right? We rarely would put parenthesis x squared plus y squared plus z squared. That's the three-dimensional equivalent to the Pythagorean theorem for r squared. Right, well, so r squared is equal to x squared plus y squared plus z squared. We could put that here. But we never do. We never do because it's simpler to just put r squared. But because we're in a different coordinate system, we're in now a spherical coordinate system. Spherical coordinate system has three coordinates that are mutually perpendicular, but it seems wrong. One of the coordinates is the radius. What direction does the radius point? It points whatever direction you're looking, and then we have two other variables that describe that direction. So radius is in and out, and then we have theta, which now I have to get these straight. I believe theta is measuring the angle from the z-axis. So it's measuring from vertical down. And you will see different definitions for theta and phi in different textbooks. So you have to be a little aware of what your textbook's definitions are. But I believe theta is going from vertical to down, and phi then is going all the way around the circle. I hope I remembered which one is which correctly. It does not matter for today, but it does for most cases. And so the gradient operator is a much more complicated looking beast. I don't like to use that gradient operator. When we get to quantum mechanics, we have to use it for a hydrogen atom because you know what the hydrogen atom has? Spherical symmetry for this force. So we find the spherical harmonics using the spherical version of gradient. So what we're going to do now is once again check to see if this is a conservative force or not. So what was the method to check to see if it's a conservative force? Calculate the
Gravitational force.
Well, we're going to check to see if this gravitational force is conservative.
Okay.
The way to check is what it says here. You calculate the curl, which means you check, that's the curl. If the curl is 0, then it's conservative. So I need to check that. So we've already done it twice. How do I do this curl calculation? I don't want to slide it over there and show you. I want you to tell me before I do that. How do we calculate the curl? You make a what? It's a determinant, not a matrix, but I'll go with you on that. We take the determinant of a matrix, right? So we're going to take a determinant and now my directions, instead of x, y, and z, are going to be r hat, theta hat, and phi hat. There we go. And now I put the components. My force of gravity. First we have to put in the gradient component. So what's the component in the r direction for del, for the gradient? ddr. What about in theta direction? 1 over r dd theta. And what about the phi direction? All right, and then we do the force. Fortunately, this force is one-dimensional. And now I have to evaluate this. R hat was the first unit vector. What's the determinant of its comatrix? Since these are both 0, it has to be 0 because you can have 0 for every term. Remember, every term has one thing in each row, also one thing in each column. Yeah. So you're going to have this times that, or excuse me, this times this plus this times this. Both of them are multiplied by 0. So that's going to be times 0. And then we have minus theta hat. And this one is going to have, of course, dr of 0, ddr of 0 is 0. But we're going to have 1 over r sine theta dd phi of minus gm1m2 over r. The cool thing is, it's a partial derivative. We're taking derivative with respect to phi, and there's no phi in the r component of the force. Does everybody see that? Or should I write this out? Okay, I'll write it out, and I'll write it out in longest form possible and then in the intermediate form. And then expanding that, so the first term is clearly 0. ddr of 0 is 0. The second term is taking derivative with respect to phi of minus gm1m2 over r squared. There's no phi in the thing I'm taking the derivative of. And since it's a partial, I'm treating the r as a constant, so I'm taking the derivative of a constant. And we take a derivative of a constant. It gives you, what net value does it give you?
Derivative of constant.
Yeah, 0. And so that's why I get 0. I've shown the longest way, the intermediate step, and then the final step. And for my last term, plus phi hat All right, what's the derivative with respect to r of 0? The partial derivative with respect to r of 0 is? Which one? 0. And what's the derivative with respect to theta, partial derivative with respect to theta, of minus gm1m2 over r squared? So, in the end, it's equal to 0. That's how we show that it's a conservative force. Once we know it's a conservative force, then we can go ahead and calculate the potential energy that goes with it. So to calculate the potential energy, different coordinate system means a different dx vector. So for spherical coordinates, I put dl instead of dx here. The DL is r hat dr plus theta hat r d theta plus phi r sine theta d phi. Once again, any normal person's like, really? Did it have to be so difficult? It's math. Did it have to be? I guess the answer is yes. So now we do the integral. And I'm just putting from A to B. Fortunately, the dot product is simplified. What, again, does it mean to have a dot product? Right? We're going over cross products and dot products like crazy today. What does the dot product mean? Parallel parts. So the force was only in the r direction. So what's parallel to the r direction? It's only dr. The other things were perpendicular. So since we're only doing the parallel parts, this drops down to a much simpler integral. Thank goodness.
So you can only do dot and cross products one at a time.
Well, for the work calculation, it's an integral of force dot distance. So that's why we're doing a dot product. We do have equations that combine dot products and cross products, and they make life just a little more hairy. So yes, we can combine them.
So how did you get the second part of the equation for the integral?
That was the DL, right? Integral of force dot DL. DL in spherical coordinates is that second part.
Okay, are we ever going to be able to find that on our own? Or is that
You will never be able to, or have to find it on your own from my class.
okay.
And since you're not taking calculus with the gentleman here, you will have to do it.
Okay.
They will have to do it either this semester or next semester. They'll have to derive where it comes from.
Okay, and I won't.
No, well, it won't be in physics. It'll be in their calculus class.
Oh, okay.
Yeah. And in the physics test, you'll just be given it. I don't expect you to derive it or have it memorized.
Okay.
So now we have a fairly easy integral. What's the integral? Right, g, m1, m2, those are constants. What's the integral of dr over r squared? Hopefully you're not like me and have your brain backfire like mine just did.
dr cubed over.
That's what my brain did, but it's not. This is r to the minus 2. You raise the power by 1 and divide by the new power. So it's going to be notice I have a minus and a minus. So there I've put in my limits. Now that's equal to the work. What's the relationship between work and potential energy? There's a minus sign. Change in potential energy is defined as minus the work. So that means potential energy B minus potential energy A is equal to minus parenthesis G M1 M2 over RB. And so once again, by identifying potential energy B must be this term, keep in mind there's a minus sign, so we get potential energy is equal to minus G M1 M2 over R. And as always, we could put plus a constant with it. We don't. We just put a 0 for the constant. So that's how we get the gravitational potential energy for the general gravitational force. First, we had to check to make sure that it was conservative. Then we went ahead and did the calculation because it was conservative. So now, given something that is not a standard force, some contrived force that I made up. So we're going to check this to see, is it conservative? So why don't you three work together here and see if it's conservative. Talk to each other. I will start by asking, how do you determine if it's conservative?
If it for directions isn't
Mathematically, we do that del cross F, which as Nathan says, the determinant. So set that up. Notice this is Cartesian coordinates. No crazy spherical coordinates. There's no need to make the problem unduly difficult. It's difficult enough, right?
What's next to it? So x squared for x.
No. That's the bottom one.
Which one?
The middle row needs to be the ddx, dy, dbc.
Okay. Yeah, so
How do we find the derivative of an equation like this? In the last few they were given.
The what?
The partial derivative they were given.
Oh, the gradient. This is Cartesian.
Oh, gradient,
So
sorry.
the Cartesian gradient is going to be this one right here.
So it's going to be the same no matter what.
Yes, it's Cartesian. It's
Okay.
always going to be that.
Oh, okay.
So that's what you're putting for your second row.
Got it.
what's it d?
Yes. Make sure it's the partial, so the final
Partial.
curve leaves. And then, looking at this, what were you saying, Nathan? Nathan was quoting.
It was when you times it by.
Well, no, now you're putting in
Or,
the
I
final
mean, yeah,
row.
okay, that's, I mean, like what you're putting in what it's times each direction.
Yeah.
It's times by. So which direction?
So ax squared.
So under x of a is
That's right.
x squared. Yeah, And then minus, yeah, minus
over
1.
y over y.
Let's see why. Let's see.
All right, now you do your determinant. Caitlin's already well along the path. That's all correct. Notice the important things that she did. She has the signs positive, negative, positive. She has the signs positive, negative, positive. That's an important thing that's easy to forget. We have the 11-7 symbol that we use to keep track of that, but there's no point in bringing that up. And then she has, this one didn't have the A column, so it has the B and the C columns. This one didn't have the B column, so it has the A and C, so it didn't have C.
You know partial derivatives then?
Who else? Yeah, that's next.
Oh wait, this is one. No,
That's a line, the last one's supposed to be a C. We are past time. If you have to run, you should run. But you've already run into ddy of cy. What's that?
Maybe why? Because there's
C.
a C constant, which is then 0 because of it.
No, it's C.
What do you mean?
Well, the partial derivative with respect to y of cy
Is C.
is C.
Okay.
And so it's not going to be 0.
Maybe it's not conservative.
Right. Right. Now, you do need to go on and make sure this one is, if this one here was a minus C, then it could still be 0, but it's not going to be.
Yeah.
Okay.
This is C.
And so you don't even need to go on. Once you have one component that's not 0, it can't be 0. Okay, so I was going to go on then. I had another one for you to do that has a z times the c instead of a y, and then it turns out that that's conservative, and then you calculate the potential energy, but we don't have time.
Okay.
All right, I'll see y'all for lab.
It'll be an interesting one too.
Yeah, we're going to make things bang into each other.
You have time to go over that with me real quickly? I'm having a hard time finding my pre-lab stuff before.
I certainly do have time.